Okay, so still on proof by divisibility, we're going for example 3. So prove by induction that n squared plus 3n is divisible by 2 for all n element of n or all n element of natural numbers. This one is slightly different compared to the last two examples in that we don't have n as a power, and in the last two examples we had a minus and then we've got a plus. So for us to know that it's proof by divisibility is what they'll do is they're going to tell you it's proof by induction by divisibility. And in this case we're looking at 2. Last time we had divisible by 3, and before that we had factor of 3, so now we've got 2. So the number that is you're looking at, or the factor you're looking at here being 2, that can change throughout every question. So you could get like divisible by 6, divisible by 4, by 8, by 10. So that does change. This number changes depending on the question. So we'll start with to prove. So proposition n squared plus 3n is divisible by 2 for n an element of n. And we'll start with our first step. So P1 for n is equal to 1. And we'll sub in 1 for n. P1, 1 to be squared plus 3 times 1. Proposition 1 is 1 plus 3. Proposition 1 is 4. And we want to know if that's divisible by 2. So divide by 2 and we get 2. So therefore, 4 is divisible by 2. And proposition 1 or P1 is true. So that's our first step for this question. And the last question we had 3 divided by 3 gave us 1. So for this, as long as the number for P1 is divisible by the number they gave you in the question. So for here, 4 is divisible by 2. They could have said 8, and that's divisible by 2. So as long as the number that is when you sub in your 1 is divisible by the number in the question, then you're happy to go for P1. So second step then is assume proposition k is true for n is equal to k. And we'll fill in pk, which is k squared plus 3k. And we're assuming, so proposition k of k squared plus 3k is assumed to be divisible by 2. And because we're assuming it's divisible by 2, we can say that k squared plus 3k is equal to 2 times a, where a is the element of z. So 2 times a, like the last time, this is a multiple of 2. And if the left-hand side is equal to a multiple of 2, then it has to be assumed divisible by 2. And then we're going to isolate k squared, and we'll have 2a minus 3k. That's going to be our second step. Third step then is our prove that proposition k plus 1 is true, given that n is equal to k is true. So prove that the proposition k plus 1 is true, given that n is equal to k is true from our first step. And we'll sub in k plus 1. pk plus 1 is k plus 1 to be squared plus 3 times k plus 1. And we're just going to tidy that up a bit. K squared plus 2k plus 1 plus 3k plus 3. So we're still just tidying it up a small bit. K squared plus 5k plus 4. So that's that tidied up. And now we're going to use our last line in step 2 for the last line that we have here for 3. So we know that k squared is equal to 2a minus 3k, and we've got k squared in our third step here. So we're going to let this be substituted in for k squared. So proposition k plus 1 is 2a minus 3k plus 5k plus 4. Again, we're just tidying up. 2a, so minus 3k plus 5k plus 2k plus 4. Factorise out 2 then. 2 bracket a plus k plus 2. And again, like before, we're going to let this bracket equal to another number. So we'll say equals 2b, where b is an element of z. And our conclusion then for step 3, pk plus 1 is true, having assumed pk is true. And we have our conclusion then, 4 for conclusion. And we're just copying what we have for the first bit. So P1 is true. And then if PK is true, then PK plus 1 is true. Move that up a bit. So in step 1 we've got proposition 1 is true, then we're taking if proposition of k is true, then proposition k plus 1 is true, and therefore by induction proposition of n is true for all n element of n. And that's our conclusion for our example 3.